Good morning everyone, my name is Douaki and I'm a PhD student at the Free University of Bolzano, and today I will present to you my work on carbon nanotube ammonia gas sensor, a comparative analysis between impedance spectroscopy and resistive measurements. So first I will give you a general idea on why ammonia sensing is important, and then we will see the fabrication process of the device used in this work, and then after that we will discuss some results, and finally wrap up with the conclusion. So ammonia is a highly toxic chemical substance common in biological processes and applied in technical installation processes such as chemical industry, motor vehicles, and cooling systems. And also ammonia is used for the production of nitrogenous fertilizers. So due to the high usage of ammonia, the American Conference of Industrial Hygienists has set a limit to ammonia concentration in air of 35 ppm for 15 minutes exposure and 25 ppm for 8 hours exposure. So any exposure to ammonia for a time or for a concentration higher than these values, it can cause eye irritation, skin irritation, and lung diseases. And also during the food spoilage, mainly meat products, the food releases different gases, and one of these gases is ammonia. Hence, by monitoring the presence and the concentration of ammonia inside the food packaging, we can get an information and we can monitor the quality and the freshness of the food product. Also, the ammonia released from animals' waste from fertilizers can combine with the volatile organic compounds, nitrogen oxides, and sulfur dioxide in the air to form health-harming small particles. Therefore, the design of novel techniques and sensors which allow accurate and fast detection of ammonia concentration is highly desirable, and such sensors should satisfy the specific requirements such as high sensitivity, enhanced selectivity, and low energy consumption. So currently there are different types of ammonia gas sensors ranging from resistive sensor to acoustic wave sensor to catalytic sensor, also with different materials. And every material or every type of ammonia sensor has some advantages and limiting factors. And currently the most used gas sensors is the metal oxide gas sensors, and this is due to their simplicity and low fabrication cost. However, the metal oxide gas sensors, they lack the flexibility, and they suffer from high operating temperature, which leads to a high energy consumption, and also they suffer from low sensitivity and selectivity. Hence, an alternative gas sensor or material that can be used at room temperature with improved sensitivity will be desirable. And this is what carbon nanotubes of gas sensors offers due to their working at room temperature ability. However, they lack also the selectivity and sensitivity. So in this work, we developed a resistive carbon nanotube ammonia gas sensor, and we compared between two different measurement techniques, namely conventional resistance and impedance spectroscopy. So here we have the fabrication process of the gas sensor, where the interdigitated electrodes were screen printed using silver ink, and then carbon nanotube water-based solution was which used as a sensing material was spray coated using spray coater. And here we have the measurement setup where we have the flow meters to control the flow of ammonia and nitrogen, which I used as the carrier gas. And then we have the testing chamber where the ammonia gas sensor was exposed to ammonia. And also we have the network analyzer. So here we have time response of carbon nanotube gas sensor to ammonia when conventional resistance was used as the measurement method. And we can see here we have the normalized resistance versus time. And we have these red zones, which is the sensing intervals where the sensor was exposed towards ammonia for 5 minutes. And we can see that the concentration was increased from 15 ppm to 90 ppm with a step of 15 ppm. And here we have the calibration curve towards ammonia, and as we can see here we have the normalized resistance versus ammonia concentration. And as we can see, when ammonia concentration was increased, the normalized resistance was also proportionally increased. And we got a sensitivity of 0.266 and coefficient of determination of 0.97. Here we have the response of carbon nanotube gas sensor to ammonia, where the impedance spectroscopy was used as the measurement method instead, or the measurement technique instead of the conventional resistance. So here we have the modulus versus log frequency. So at the end of the sensing interval, the frequency was swept from 5 Hz to 6 MHz and the modulus was registered. Here we have the calibration curve towards ammonia by taking the modulus at 5 Hz. So as we can see, the normalized modulus was increased when the concentration of ammonia was also increased. And we got a coefficient of, we got the sensitivity of 1.23 and the coefficient of determination of 0.99. So here we have a table which summarizes the results obtained from this work. So when the conventional resistance was used as the measurement method, sensitivity of 0.266 and R-square of 97.56% were obtained. And then when impedance spectroscopy was used as the measurement method, the sensitivity obtained was 1.23 and R-square of 99.66%. And compared to the literature where a flexible carbon nanotube gas sensor was developed and conventional resistance method measurement was used, the sensitivity of 0.24 was obtained and an R-square of 94.28. So as we can see, when the impedance spectroscopy was used as the measurement method, the sensitivity was increased from 0.26 to 1.23 and the linearity of the response was improved also. So to understand what happens when the carbon nanotubes are in contact with our gas, so in the presence of ammonia, which is a reducing gas, the gas molecules directly adsorb onto the carbon nanotube's surface, inducing electron transfer and changing the electrical conductivity of the nanostructure. And then the NH3 donates electrons to the single-word carbon nanotube, which in turn modifies the density of free charge carriers in the single-word carbon nanotubes. And as the carbon nanotubes used in this work behave as a p-type material, the donated electrons recombine with the free holes, hence a reduced carrier concentration results in an increased electrical resistance, which is proportional to the concentration of the NH3 molecules absorbed on their surface. So when when conventional resistance was used, the change was evaluated. The change induced by the gas molecules was evaluated only in terms of conductance, but when impedance spectroscopy was used, the change induced by the gas molecules was evaluated both in terms of conductance and reactance, and gave us more information and increased the sensitivity. So to conclude, we can say that in this work, flexible carbon nanotubes ammonia gas sensor was developed, and also changing the measurement technique from the conventional resistance to impedance spectroscopy give us more information on the change induced by the gas molecules. And also for future work, we can improve the selectivity of the carbon nanotubes gas sensor by tuning the frequency for each gas. And thank you very much for your attention.